Okay, so for those of you who are not so familiar with the area, ophthalmic imaging is commonly used in the clinic, but it's based on an old technology, and it's based on single element transducers. That's the primary product in the market. It's because they're inexpensive, and there hasn't been much development really in years other than small incremental improvements on SNR and lowering the cost. And so the devices are single element, they're linear sector scans with handheld probes, and they're optimized either for the front of the eye around 40 megahertz or the back of the eye around 20. So they don't have very good depth of field because it's a focus transducer, so there's always a compromise there. And that means the user either has to be good at putting the focus where they want to image, or the way the system is set up, it's in contact with the eye somehow, and the focus is at some fixed distance, which actually could be a problem if you have someone with myopia, for instance, where they have a long axial length. It'll shift the focus from where you would typically find it. So there's no way to image the full globe, really, at this point, or to get good images of the vitreous. So annular arrays are a nice step forward, that they're still pretty simple, a low channel count, they're not as complex as a linear array system, which means they're not as expensive, and you get a very good depth of field, a good resolution over that depth of field, and you get a radial symmetry in the beam, so it's really the highest quality beam that you can get, but you still have to mechanically scan these, so there's some compromise there. And so this is just a quick diagram just to show you kind of what's going on here. In this case, let's say we have a 5-element annular array, and we're using what we call synthetic focusing, where we're really acquiring individual transmit-receive pairs and then doing beamforming, so very basic beamforming here, because it's easier to do that than try to transmit with very, very small delays and focus at some depth. And so what you do then when you go through the processing is you end up with a nice beam, as we show here. So this would be a fixed focus case with the same geometry, where you have the narrow beam at the focus, and it expands in classic beam shape. And when you do the synthetic focusing, you more or less get an increasing F number with depth, and so you can see it narrows. And as you get further away, it's going to expand. And so then moving on into our system, this has been covered in various forms in the past, so I'm just going to quickly step through it, and I'll talk about the actual fabrication of the transducer. But we, in this case, it's a 5-element array with about a 26-millimeter focus, and the aperture, the total aperture is 9 millimeters. It's based on a 25-micron VDF-TrFE film, which is press fit and given a spherical curvature. And we use a flex circuit as the base layer of this, in a sense, that we press the PVDF into. And so after the press fit and the process of making it, we end up with something like this. We have an epoxy-backed device that gets further packaged into a little stainless steel shell in this case. And that was then put into a handheld probe that is a commercial probe. I'm not going to say much about it, but it's a probe that's used for ophthalmic imaging on the market now. And we modified this probe to run a cable outside, and so we can get a fairly large radius of curvature. We had some problems with shearing of the cables, trying to package it really tightly inside, so we just put this thing on the end. This piece gets filled up with water. I'll show you a picture in a second, and we do what's known as contact scanning in the ophthalmic market. And so this is the clinical system. It's not a beautiful piece of equipment that you would market with a picture like this, but this is what we use in the clinic at Columbia University, where Ron Solerman works. And so this could be prettier, I'll admit that, but we have all the components here of a system. We have our pulsar under here, the 5-channel pulsar, a control PC with the digitizer card, the module that controls the handheld probe is shown here, and it's been modified just to perform the motion part of the system, so it's not being used in its pulse receive mode as would normally be done with the actual product that's sold. And we have some cabling here that does the transmit timing for the different elements. And so when this is used on a patient, what we have is shown in the diagram here. We have the handheld probe that would be placed in contact, and it can be done through the eyelid, or the eyelid stretched open a little bit, and the membrane can be pressed right against the sclera for the imaging. And we typically go through the sclera rather than the lens, because the lens tends to distort a little bit of the image. And so just to provide a bit more detail on the system, it's all a LabVIEW control, not real-time LabVIEW, but just the normal LabVIEW package. we're using a Daxonics 5-channel pulsar. And the handheld probe, some of the characteristics are it's a linear motion path, about a 16 millimeter lateral distance for the full scan. It operates through a circular motion internally, and that translates into a sliding motion of the transducer through some gearing. There are Hall effect sensors that provide feedback on position, and then there's a lookup table that's used to provide the spatial triggers. And so we have some control on that. And then the spatial triggers from the probe then move into our electronics, and we use that to start our sequence of triggering for the elements. And we're just using a timing card from National Instruments to create a series of delayed pulses to transmit on individual rings, where we just add enough time to allow a round-trip transmit event. And so we can transmit on 1 to 5 elements, however we want to set it up. And then we receive on just 4 of the channels, because the 4-channel card is just the limitation there, and there was no point in buying a second card just to get 1 more channel. And so we basically can transmit on any of the 5 elements, 1 or 5, and we can receive on 4, so we can run through any combination of those. And we do the beamforming right now just on the CPU. And this card from Alizar-Tech is a PCI Express card, so it pretty much just dumps the data into the computer RAM. And so after much trial and error and quantifying how this thing works, we found the best parameters after all the compromises were using 3 transmit events. So we transmit on 1, then 2, and then 5, and so again in a delayed sequence, and each time we transmit, we receive all 4 channels. And we were able to get 140 lines, and that in this case was about 117 microns between the lines, and the probe operated about 4 frames per second. And then we can use this in a handheld fashion, and this is an example of a wire phantom where we just have a wire in long ring. We're holding the probe and moving it up and down, and this is a 25 micron wire. And so the frame rate here is not limited by intrinsically anything that means a fundamental limit. It's really the probe that we're using that limits the frame rate. We're just stuck in a sense with what we have. And one of the limitations of this probe is it only creates triggers in one direction. So if that could do that in both directions, we would double this frame rate right there. And we then went through some characterization just to make sure things were working as expected. And so in this case, we're taking lateral scans, point spread function of the wire. And in this case, it was really a careful study where we attached the probe to a stage, move the stage in very fine steps. So it's not the probe moving internally, it's an external movement, because that way we can get a very small step size. And we're comparing then these measurements, which are the dots, with theoretical predictions. And so here is the axial depth. This is the 6 dB lateral beam width. And I'm showing 2 curves here. One is the theoretical curve if you're transmitting on all 5 elements and receiving on 4, and one is if using our sequence, just to show that even though we reduced a little bit the transmit aperture in a sense, the change in the beam width is rather minimal. And the next study was letting the motor operate and just seeing what happens with these wire measurements. And not surprisingly, because we have a very large step size, again, a scan here, things were spread out. And so what we're looking at here is the axial depth, where we have the wire at one fixed step, and we're moving the wire left and right and taking repeated measurements and characterizing the beam width, doing that at 4 depths in this case. And what you see is, because we have a fairly big step size, getting a very accurate measurement of the beam width is more difficult, but also this is an indication that there is some instability just within the system that we're using in this case. In that each time it makes a pass, there's small changes in the spatial trigger location, and that's reflected in the measurements here. And so we then went and looked at 2 of these depths just to look at if there was a dependency on position in the image and the beam width measurements to make sure there wasn't a bias within the image field. And what we see is that there's really more or less a uniform spread in the beam width wherever you are. So basically a fit would just be a horizontal line here. So we're getting equally bad resolution, or you could say equally good resolution regardless of where we are. And finally, before we use this in the patients, we had, of course, characterized the acoustic pressures to get approval to use this on human subjects. And so we just went through and made the standard measurements of the peak pressures at the focal position, and just to ensure that we're below the limits. And so I won't show the numbers, or discuss them in detail, but suffice it to say they're all below the FDA limits for what is required to use this on human subjects. And so finally then we took this up to the clinic and started some of the initial scans. And so again, this is the handheld probe using a contact scan, and that the patient will sit and tilt their head back slightly during the scan. This image is a 50 dynamic range. Again, we're at 4 frames per second. And so what is noticeable right away for those of you who are familiar with these images is that we're really seeing the full eye from front to back, which typically you would not see with an ophthalmic system. You would see just the anterior segment in detail or the posterior, but you never see both in nice focus. And then you can see this is the eyelid up here, and we have the iris and sclera visible, the retina in the back. So more or less a standard clinical image, you could say. And there's some other examples here where we haven't really done detailed studies yet looking at patients with certain conditions, but from the scans we've taken, we've started to just examine how this probe is working, and this is an example of a patient with a PVD, and the contrast here is a little harder to see, but there's some reverberation echoes that come in here in the middle of the vitreous, but down here, you'll notice there's some echogenic regions, and that's a posterior vitreous detachment of the patient, and there's some floaters in this patient too, and just to note that we also see the ciliary body here. You can kind of see the iris move sometimes. And on the right, another patient with a lens implant, so you'll notice there's some sort of reverberation echo here, and the iris, the lens look a little funny. And this patient is also a myope, so the axial is quite extended from what you would typically see. And as this cycles through, you'll also notice that up here, around the ciliary body, you can see the ciliary processes in some detail too, which is interesting. Okay, so that's where we are. We've got a system finally that's really a handheld probe. We've shown this in the past in various forms, but it's always been a clunkier setup where we really had to use a water bath and the patient was lying on their back, and it's not so practical. But now we have a nice prototype showing that it all works. We're using mostly off-the-shelf components. There's nothing really customized here except for the pulsar from Daxonics, but they make those quite frequently now. So in a sense, this represents a first big step forward in ophthalmic imaging in quite a while. Our frame rate, again, is limited by the probe that we're using. There's no reason these frame rates can't be higher with a probe that's designed differently. Again, our probe only creates triggers in one direction, and it has a very high velocity in the central region, which makes it hard to transmit a lot of, or transmit on all 5 elements in the middle of the image. And it also means we have to spread out the distance between scan lines to make sure there's time to do our transmit events. So above 10 frames per second is certainly feasible in a system like this, and we're still working on the scan protocols as we begin to use this. So with that, Mr. Metz says thank you, and that concludes my talk. Have I compared it? Well, there's certainly OCT is going to always win on outright resolution, but OCT cannot, it can only see through the pupil. So an OCT system will never be able to see through the sclera. And they're working on OCT that can give you a longer axial depth of field. So there will be always improvements, but ultrasound has certain advantages that relate to the penetration of light through tissue. I think it would be difficult to, with this configuration, to do it, but it's possible.
So let's give another round of applause.